You know how we're always searching for that perfect balance, like a laptop that can crunch through heavy tasks, maybe some gaming, but doesn't sound like a jet engine or weigh a ton.
Exactly.
Yeah.
And the demand for that kind of powerful and efficient mobile computing just keeps growing, doesn't it? It's not just about raw speed anymore.
Right, it's about smart power, which brings us nicely to what we're digging into today, the AMD Strix Halo processor.
You might also see it marketed under the Ryzen AI Max series name. It's AMD's new top-tier APU.
Yeah, APU accelerated processing unit. Basically CPU and pretty serious graphics all baked onto one chip. We're seeing it aimed at high-end laptops, AI workstations, even those like surprisingly powerful mini PCs.
hmm And we've been wading through, well, a lot of analysis, some early hands-on reviews, technical specs, trying to piece together what really makes this thing tick.
So our goal here for you is to unpack what makes Strix Halo different, what it can actually do, and what it might mean for the kind of device you might buy next.
And one of the first things that leaps out is this really wide configurable TDP range.
Oh yeah, the thermal design power. It goes from, what, 45 watts all the way to 120 watts?
That's right. And that huge range means performance is going to vary quite a bit depending on the specific laptop or device. It's a key characteristic.
Okay, so let's get under the hood then. What are the core components making this thing run?
Well, at its heart, you've got AMD's latest Zen 5 CPU architecture. This is a pretty big deal. Significant jumps in both performance per clock cycle and power efficiency.
And the top chip, the Ryzen AI Max plus 395. How many cores are we talking?
Up to 16 cores and 32 threads. That's desktop-level multitasking power, really, in a mobile chip. And they can boost up to 5.1 gigahertz.
Wow, 16 cores, but just having a lot of cores isn't the whole story, is it?
Yeah.
How do they access data quickly?
Good point. The cache system is crucial.
Hmm.
Strix Halo uses dedicated L1 and L2 cache for each core, which is super fast memory right next to the core itself.
Okay.
And then there's a large shared L3 cache up to 80 megabytes on that top model. Keeps frequently used data close, speeding things up a lot.
Makes sense. And I saw something about AVX 512 support. That's more for specific heavy-duty stuff.
Exactly. AVX 512 instructions can give a real boost to certain professional workloads. Think scientific computing, maybe some high-end video encoding, that kind of thing.
All right, so the CPU side sounds, well, beefy, but it's an ATU, so the integrated graphics are a huge part of the story here, right? I've heard some pretty wild claims.
You heard right. The graphics side uses AMD's RDNA 3.5 architecture, and it's a massive upgrade from previous integrated solutions.
How massive are we talking?
The top configuration gets up to 40 compute units. That translates to 2,560 stream processors. These are the little engines doing the graphics work, clocking up to 2.9 gigahertz.
Okay, that sounds like a lot for integrated.
It is. And it's not just raw power. It also includes dedicated hardware accelerators for AI tasks and for ray tracing that tech that makes lighting in games look super realistic.
So the performance is potentially stepping on the toes of dedicated laptop GPUs.
Potentially, yes. We're seeing performance that genuinely rivals some mid-range discrete laptop graphics cards. It's a significant step up for what you can expect without a separate GPU chip.
Okay, integrated graphics competing with dedicated cards? That is interesting. And AMD seems to be leaning heavily into AI with this chip, too. There's a dedicated part for that.
Absolutely. It features the XDNA2 NPU neural processing unit. It's a specialized engine built specifically for handling AI workloads efficiently.
How efficient? What kind of performance does that NPU bring?
It's rated at over 50 TOPS. That's tera operations per second. Basically, it means tasks like natural language processing, image recognition, stuff like that. They can run much faster and use less battery power compared to running them on the main CPU or even the GPU.
So you've got this powerful CPU, really strong integrated graphics, and a dedicated AI engine all on one piece of silicon. It sounds like they really threw everything at this.
Pretty much the kitchen sink, yeah.
What about memory? That's often where things get bottlenecked, right? Especially with integrated graphics sharing system RAM.
AMD definitely focused on that. Strix Halo uses high-speed LPDDR5X memory up to 8,000 megatransfers per second.
Fast RAM.
Very fast. And crucially, it's on a really wide 256-bit memory bus. Think of it like having a huge highway for data instead of a narrow road. This allows for massive bandwidth.
And capacity. How much RAM can these systems support?
Up to 128 gigabytes, which is, again, huge for this class of device. The key is the unified memory architecture.
Ah, right. So the CPU, the GPU, the NPU, they all share that same big pool of fast memory.
Exactly. No need to constantly copy data between separate memory pools, which saves time and power, especially for things like gaming or significantly running large AI models that need tons of memory.
That makes intuitive sense. A shared fast pipeline. Now, physically, I read it's a chiplet design, not one single slab of silicon.
Correct. Instead of one big monolithic die, Strix Halo uses chiplets. Think like Lego bricks. It usually helps with manufacturing yields and allows mixing different process nodes if needed.
So what are the bricks here?
You have two Zen 5 core complex dies, or CCDs. These contain the CPU cores, up to 8 per CCD. And then there's a separate large I/O die.
And the I/O die has everything else.
Pretty much. The RDNA 3.5 TPU, the XDNA2 NPU, the memory controllers, display outputs, PCIe lanes. All the connectivity stuff lives on that I/O die.
How do they connect these chiplets together? Is it fast?
They use a parallel sea of wires interconnect. It's different from the high-speed serial links, the SerDes, used in their desktop chips. This approach is optimized for lower latency and lower power, which are really important for laptops and mobile devices.
And it's all built on what process node?
TSMC's N4 process. It's a mature 4-nanometer node offering a good blend of performance and power efficiency.
Okay, quite the technological package. Let's circle back to that TDP thing, 45 watts to 120 watts. That's a massive swing. How does that actually play out in terms of performance we can expect?
Right, so the TDP directly impacts the sustained clock speeds of both the CPU cores and the integrated GPU. At the lower end, say 45 watts, the chip has less power budget to work with.
Meaning things might slow down under heavy load?
Potentially, yes. The CPU might not be able to maintain its highest boost clocks, especially if all cores are active. And if the GPU is also working hard, say in a game, the power might need to be balanced, possibly limiting the CPU even further. You might hit what some call CPU core starvation under heavy combined loads.
So even with 16 cores, you might not get the full benefit if the device maker sets a low TDP limit to, say, fit it in a thin chassis.
Exactly. But flip that around, push the TDP higher toward that 120W mark.
And everything gets faster.
Significantly. The CPU can sustain higher clocks for longer, boosting multi-core performance. And the integrated GPU, the RDNA 3.5 part, really stretches its legs. Higher TDP means higher graphics clocks, potentially using more of those compute units more effectively. You see clear gains in gaming frame rates, GPU compute tasks. Benchmarks like 3D Mark show this scaling very clearly.
So the laptop makers, the OEMs, they have a lot of control here. They're managing this power balance between the CPU and GPU depending on the device's cooling and target market.
Absolutely. They implement power management algorithms to shift power dynamically. You might be editing video, primarily CPU-bound, then switch to a game, and the system tries to allocate power optimally.
And that fast wide memory bus we talked about is still crucial across this whole range.
Oh, absolutely vital. That LPDDR5X running at up to 8,000 MTs on the 256-bit bus, that feeds the beast, especially the hungry iGPU and the NPU for AI tasks. But even with all that bandwidth, if the overall TDP limits the power, the components can't run flat out, so you might not fully saturate that memory bandwidth potential.
Gotcha. It's all interconnected. Even the NPU's sustained performance in long AI jobs will likely be influenced by the available power budget, right?
For sure. While it's designed for efficiency, demanding continuous AI workloads will still draw power, and that comes out of the total TDP pie.
Okay, performance scales with power. Makes sense. How does Strix Halo actually stack up against the competition then? What are the benchmarks telling us so far?
Well, on the CPU front, particularly in multi-threaded tasks like Cinebench, Strix Halo looks very strong, often beating Intel's Core Ultra chips, mainly thanks to having more cores in its top configurations.
What about single-core speed?
That seems a bit more variable. It's competitive, but results can depend on the specific benchmark and how well the chip sustains boost clocks within its TDP limit. But the real headline grabber is the integrated graphics.
The RDNA 3.5 part again.
Yeah, it's consistently showing performance comparable to mid-range discrete laptop GPUs. We're talking NVIDIA RTX 4060 laptop level, sometimes even pushing towards the 4070 laptop, especially when it's allowed to draw more power.
That's pretty remarkable for graphics built right into the main processor. I think I saw some testing from the Fox on an early device, the Asus ROG Flow Z13.
Yes, that was some great early data. They found the Strix Halo APU in that machine delivered roughly double the gaming performance of AMD's previous best, the 780M, when running around 20-25 watts.
Well, okay.
But they also noted a significant performance drop when they forced it down to 15 watts. So there's definitely a point where starving it of power really hurts that scaling.
Makes sense. And what about AI? You mentioned the NPU.
Right, the XDNA2 NPU. This is where things get really interesting, maybe even disruptive. In certain AI tasks, specifically running large language models, LLMs.
Like ChatGPT style models.
Exactly. Strix Halo has been shown in some tests to actually outperform high-end desktop GPUs like an NVIDIA RTX 4090.
Wait, seriously? How is that possible?
It comes down to that unified memory.
Mhm.
The Strix Halo chip can access up to 128 GB of fast system RAM directly. Large AI models need huge amounts of memory. A desktop card like the 4090 has, say, 24 GB of dedicated VRAM. If the model doesn't fit entirely in VRAM, the card has to constantly swap data back and forth with system RAM over the slower PCI bus.
Ah, so Strix Halo avoids that bottleneck by having direct access to a much larger memory pool, even if the raw compute isn't as high.
Precisely. For certain memory-bound AI inference tasks, that unified access to potentially massive amounts of RAM gives it a huge advantage over discrete cards with limited VRAM. It's a fundamental architectural benefit for specific workloads.
That's genuinely mind-blowing. An APU outperforming a top-tier desktop card in specific AI scenarios. Okay, let's look at some of the numbers we've seen. What jumps out from the comparison data?
Okay, so in 3D Mark Time Spy graphics, we see scores trading blows with an RTX 4070 laptop GPU. That's impressive context.
Right.
Cinebench R24 multi-core shows it well ahead of competitors like Intel's Core Ultra 9 288V and even Apple's M4 Pro. Massive multi-core grunt there.
And the AI thing.
The Llama 7dB inference test showed speeds up to 2.2 times faster than that RTX 4090, specifically when Strix Halo was running at a 75W TDP, that unified memory advantage in action.
What about gaming? Real games.
Yeah, looking at titles like Cyberpunk 2077, Starfield, Baldur's Gate 3, at reasonable settings, maybe 1080p or 1440p, the performance is often comparable or sometimes better than an RTX 4070 laptop. Playable frame rates are definitely achievable. Some leaked 3D Mark results even put it right alongside the RTX 4060 laptop.
And I saw a note about Helldivers too.
Yeah, a simulated test suggested around 70 FPS, which is quite playable, at a surprisingly low 18W TDP. That points towards pretty good efficiency at lower power levels too, potentially.
It seems genuinely versatile. Strong CPU, killer integrated graphics for gaming and creative work, and potentially class-leading mobile AI performance. But there's always a but. What's the catch? Power draw, heat.
That's definitely the trade-off, or at least the major consideration. With that TDP ceiling hitting 120W, Strix Halo can consume significantly more power than older APUs that usually topped out around 3045W.
So laptops need serious cooling.
Absolutely critical. To sustain performance anywhere near those higher TDPs, devices need robust thermal solutions. We're talking dual fans, maybe vapor chambers, good heat pipes, quality thermal paste. All that becomes essential to prevent the chip from overheating and throttling back its performance.
Like that Asus ROG Flow Z13 you mentioned probably have.
Exactly. That's designed as a high-performance gaming tablet, so it has cooling to match.
Yeah.
Without good cooling, you simply won't see the full potential of Strix Halo, especially at those higher wattages.
So we might see chunkier laptops, or at least laptops with more aggressive cooling designs, if they want to unleash the full power.
It's likely yes for the top-performing models. However, it's worth noting that even with higher peak power draw, the performance per watt can still be very competitive, maybe even superior in some cases, like those AI tasks.
Right. It depends on the workload and how efficiently the architecture performs the task.
Precisely. But the user experience regarding heat and fan noise will heavily depend on the specific device implementation and what TDP profile the manufacturer targets. That ROG Flow Z13, for instance, apparently can sustain up to 80W in its manual mode.
Okay, so the chips are out there or starting to appear. What kinds of devices are actually using Strix Halo right now?
Well, early days still, but we're seeing it in laptops, like that Asus ROG Flow Z13. Reviews praise its performance, often hitting those high sustained TDPs.
But battery life takes a hit under load, I imagine.
That's often the trade-off with high performance, yeah.
Yeah.
Pushing 80 watts is going to drain the battery faster than running at 25 watts. We're also seeing it pop up in the mini PC space.
Oh yeah, like those little NUC style boxes.
Exactly. Companies like GMK Tech with their EVO X2, Framework has announced a desktop mini PC option. Pellet has one called the Y01. These mini PCs often have a bit more room for cooling than ultra-thin laptops.
So they might be able to run Strix Halo closer to its maximum potential more consistently?
That's the idea. They could offer near desktop levels of performance in a really small footprint.
Mm.
Some are even being spec'd with that maximum 128 GBs of RAM, positioning them as, pretty premium, powerful little machines.
So that wide TDP range really does let it fit into different form factors and meet different needs.
It seems so. High TDP for gaming laptops and powerful mini PCs doing content creation or AI work. Lower TDPs for thinner, lighter machines aiming for a balance of performance and battery life. It's quite versatile.
Looking ahead then, what's next for AMD in this space? Is this the peak or is there more to come?
Oh, AMD is definitely not stopping here.
Yeah.
They're all in on pushing APU performance. There are already rumors about potential X3D versions of Strix Halo down the line.
Ah, with the 3D V-cache, like they're gaming-focused desktop chips.
Exactly. Adding that extra layer of fast cache on top could give another significant boost, especially to gaming performance. And beyond that, we're hearing code names like Medusa Halo whispered for future generations, promising even more performance and efficiency gains.
Sounds exciting. But for Strix Halo itself, its success really depends on.
Well, pricing is always key. Availability needs to be good. And, crucially, how will OEMs design laptops and mini PCs around it? Getting the cooling and power delivery right to actually unlock that performance potential we've been talking about.
Right. So if we were to boil this all down, what are the main takeaways from our deep dive into AMD's Strix Halo?
I'd say the big picture is Strix Halo, under that Ryzen AI Max banner, is a really significant evolution for APUs. It seriously blurs the line between integrated graphics and mid-range discrete GPUs.
Offering impressive all-around performance.
Yeah, strong CPU, great gaming potential, and that standout AI capability thanks to the NPU and unified memory. But that performance is heavily tied to the configurable TDP.
So the actual experience will vary depending on the specific device and how the maker configured it.
Exactly. It offers amazing potential, but the implementation matters hugely.
Okay, hopefully this gives you, our listener, a much clearer picture of this important new chip and what it means for mobile computing. It really makes you think, doesn't it? Considering what Strix Halo can do, what kinds of things that you always needed a big desktop rig for might now become genuinely possible on a laptop or even a tiny PC. What workflows or games could this unlock on the go? Something to ponder as these devices start hitting shelves.